Okay. Are we ready to start? Yes, we are. So I'm giving you Alexey Goncharuk from Querify Labs, and we're starting the talk on databases. Who's operating databases? Who's a student who wants to know everything about databases? Yes, this is the correct answer.
Awesome.
Alexey, 3, 2, 1, go.
Yeah. All right. Good morning, everyone. I'm Alexey. I work at Querify Labs, and today I would like to talk to you about JIT, just-in-time compilation, and how it is used in databases to make the queries you run faster. A few words about me. I work at Querify Labs, and the company, we consult other startups and technology companies who build their own specific custom databases, and we help them to build database components, basically query optimizers, query runtimes, storage subsystem, transactional layers, and combine them in a specific way to solve their specific needs. Prior to Querify Labs, I worked at GridGain on Apache Ignite for 9 years, and I'm an Apache Ignite committer. So this talk will not be very deep. Instead, we will take a look at the core concepts and why just-in-time compilation works and how it works, and what nuances you need to know when you apply and when you work with just-in-time compilation in any of your projects, if you need. So what is just-in-time compilation? Why cannot use just regular compilation? And the reason for that is oftentimes when you just compile a program ahead of time, you don't have some specific information, and you need to build some code dispatch, some type dispatching that otherwise would take additional instructions, and your code runs slower. When you launch the program, you already have this information, and the core idea of just-in-time compilation is to take this additional info on the program, for example, the information about types of the query that you run, information about code paths, and optimize to do some code specialization to make your code run faster. And as an idea, supposedly we can, using this additional information, we can generate better code. Some of you may, if you're not familiar with the just-in-time compilation, may wonder how is that even possible. And here we can differentiate between native environments and managed environments. And in native environments, if we take aside all the complexity of generating the machine code, the concept is pretty simple. You just allocate a buffer, you put the machine code that you generated into that buffer, and you pass the control flow to that particular function. In managed environments, it's a bit more complicated because often they themselves have just-in-time compilation. So instead of generating machine code, you often would generate the bytecode of that particular virtual machine that you're running with. So for example, in Java, you generate the class bytecode and use the class loader to load the classes. And for example, in .NET, you can call assembly load with the library that you built. And once that code is generated and loaded, you again pass the control flow to that classes, to the generated code, and launch your optimized code. Why this generated code may run faster? And the answer for that is actually when you're generating JIT code, JIT instructions, you have a lot of opportunities you can take. For example, if you when you're running an SQL query and there is a filter on some column, if you know in advance that the column is not nullable, you may avoid null check that is executed for every row in a query. So when you process millions and billions of rows, that adds up to a significant speed up. When you know in advance, for example, the type system, you can not use the generic objects to represent tuples, but instead you can specialize your code to use specific primitives, which also improves the throughput and memory management. And in general, when you talk about code optimization, you strive for basically two things. You want to execute a fewer amount of code, fewer amount of instructions, and you want to execute them faster. So you want to execute more instructions per cycle. And this is and basically when you're JITing your code, we strive for these two goals. The other opportunities are, for example, when you know in advance some information about the types and the code flow, you can get rid completely of lookup tables, and even strip off the whole branches if you know that they will not be executed in advance. Now, I want to also mention two approaches that we specifically used in several projects, and they are quite different in their complexity and opportunities. I will talk about pros and cons of them later, but for now we need to know that there are basically two large approaches. Transpilation is when you generate essentially the code you would write in your IDE and then execute a regular compiler to generate the either bytecode or the machine code. Another alternative is to generate compiler intermediate representation. It is essentially a quite complex graph that represents the code flow of your program. And then to pass this control flow graph, the program execution sketch, if I may say, to the assembly infrastructure that would emit bytecode or machine code. Now let's talk about the database specifics and how exactly JIT is used in databases. First of all, to understand how it is used, we need to know how databases execute your queries. So when the query is passed to the system, the first thing that happens is that it is being lexed and parsed into an abstract syntax tree. Unfortunately, working with ASTs is not very convenient, neither for SQL optimizers nor for the query runtimes. So the next thing that happens after the validation is that the query is transformed into a tree of so-called relational algebra operators. And each of the operators has its very narrow and very specific meaning and purpose. And so to speak, there are only a handful of operators, and essentially all the complexity of the SQL queries that you write can be described as a sometimes rather large trees that use a very small set of operators. And the operators that will be of interest for us today will be mostly project. This is an operator that essentially executes expressions. For example, if you extract two columns from the database and want to sum them, the summation of the columns will be executed in the project operator. Filter operator essentially drops all the rows that do not satisfy some specific condition. And again, the condition may be quite complex, and the evaluation of that condition happens in the filter operator. So I think sort and window operators are quite understandable. The aggregation operator is one of the core operators for analytical databases, and this is the operator that does grouping and aggregation functions calculation. If you want to see examples of how this tree of operators look like, you can, I think almost every production database have an ability to look at the tree, look at the query plan. For example, in PostgreSQL, you can run explain or expel analyze, and it will drop you the relational tree with all the conditions, and explain-analyze will also tell you the statistics of the operator's execution. And for example, in Trina, you can also use explain-analyze to get the text representation of the query. And also on the web UI, you can take a look at the live query plan that is disaggregated to stages, and you can see the operator statistics and stage statistics at runtime. Now let's take a look why JITing specific operators may be beneficial. Let's start with project and filter operator. And here we have a very simplistic query with this complex expression and a filter condition. And if we want to evaluate this condition, if we would evaluate this condition in an interpreted mode, we would need to essentially traverse the tree and do type dispatch for every row in the operator. Instead, what usually analytical databases do is we decompose the relational expression tree and run the operations per vector. This is so-called vectorized execution. However, the downside of this approach is that we need to materialize intermediate results. And the more complex the expression is, the larger number of materialization you need to allocate. And this is, it gives additional pressure to the allocation subsystem and takes additional time. So instead, what we can do is we can take this particular operator and generate a very tight loop and use specific type information that is strictly narrow for this particular query. And in this example, we can assume that, for example, the rows have integer type, and we don't have any type checks. We eliminated all the null checks, and we generated the code for this particular expression. And when we invoke the regular compiler, the compiler will not, assuming that the expression is small enough, the compiler will not use any additional memory to spill the intermediate results, and the variables will be allocated directly in registers. And in our experience, and this is also confirmed, for example, by the Apache Arrow project, the switch for complex expressions from interpreted to compiled execution can have up to 2 or 3x speed up during the execution. And when using transpilation, you normally don't need to take care of the specific platform optimizations, because the compiler infrastructure that you use will take care of all necessary things. So for example, if you're running on a IVX available processor, the compiler would know that you're executing it on this processor and take opportunities to emit, for example, SIMD instructions. The next thing that we want to look is the hash aggregation and hash join operator. And again, this is a very simplistic query that can represent this particular operator. And the core data structure of any non-sorted aggregation or hash join is the hash table. And when you execute grouping on arbitrary key, you need to take care to handle that arbitrary tuples. And usually this means that you need to allocate additional memory for hash table slots, and it would also hurt the cache locality when you execute the hash lookups. Essentially during the hash table lookup, there are two things that executed on each lookup is the hash code calculation for each of the tuples that you want to put into the hash table, and then the tuple comparison. And again, since the tuple, the grouping key is arbitrary, the code that executes this hash code calculation and comparison should also handle all the type variations. what you can do instead is, again, to generate a specific data structure, specific, let's say, here you can use a struct that contains all the group key fields, and use the struct, for example, as a template parameter of a C++ hash table to generate to generate the optimized layout and optimized hash code and comparison operators for that particular query. Same things goes for example, for merge join and sorting operators, because the core thing of these two operators is the comparison function. And again, if you do not know in advance the information about the query that we would execute, the comparison function would need to handle all that complexity by itself. So instead, when you have a particular query, you can generate the code for that particular sorting key or merge key, and use it as a primitive for the sort algorithms and merge join algorithms. So essentially, in short, the key opportunity that we may take when executing relational operators is code specialization, because you know in advance the type information, you know certain invariants, for example, uniqueness of the column, or perhaps you can know that, for example, a certain column has type begint, but from the query statistics, you know that the actual range of values of this column does not exceed a byte. And using that information, you can reduce the memory consumption and even replace a hash table with a simple array for more efficient execution. Now let's, and I think it doesn't make sense for now to dig into specifics of the code optimization, because I know precisely that today there will be also a few talks about JIT and code optimizations. So instead, I would like to discuss some practical things that we faced when we were using JIT during query runtime development. And so the first choice that you get is whether to use transpilation, so essentially to generate the code, and or use the intermediate representation generation. In our practice, transpilation is quite easy to bootstrap. It's quite easy to use, because essentially you generate the code from, let's say, a template, and template engines are quite widely used and understandable. And once you generate the code, you invoke a regular compiler, and it would spill all the, essentially, it will take care of everything. It will take care of all the optimization stages. It will take care of the warnings, and it will spill the runnable code that you can plug into a system. So it's I would say that in practice, a path from not having a JIT compiler and having something that is working and generating runnable code would not exceed probably 2 weeks using the transpilation approach. The IR generation is more complex in the sense that you need to, first of all, to get familiar with the IR of the framework that you're using. You need to adjust your code to the specifics of that approach. And moreover, you need to, when you work and when you express the algorithm that you want to compile, you need to express it not in a regular code, but in the IR. This is quite time-consuming. It is error-prone, but on the other hand, it gives you very precise control over what you emit, and you can even disable certain optimization passes, because you know that you generated the IR that is already efficient. And this cuts off a lot of optimization passes and can reduce the compilation speed significantly. In our practice, the transpilation approach is more practical, so this is what we use mostly. And once you go with the transpilation, you need somehow to deal with the compilation latency, because in the relational tree you may have hundreds of operators, and each of the operators compilation time may take up to hundreds of milliseconds. And sometimes the compilation time may exceed the query runtime, so you definitely want to avoid it. And one of the optimization that can be used is so-called on-stack operator replacement. It's a let's say synonym to on-stack function replacement or class replacement in the JVM. And to understand this optimization, we need to know about streaming operators and pipeline breakers. Streaming operator it essentially does not have any eternal state, or the state may be dropped on request. An example of a streaming operator is project and filter. So essentially, when a batch of data comes into for example, to project, we execute expressions, we compute the expressions, and we emit a batch of the same size. When a batch of data, a batch of rows comes into the filter operator, we evaluate the filter, we drop the rows that do not satisfy the filter condition, and again we emit the output. So the streaming operator usually does not have any internal state. Another example of streaming operator that somewhat has internal state is pre-aggregation, but the benefit of pre-aggregation is that we can emit the pre-aggregated results on request, and it will not affect the query correctness. Pipeline breakers, on the other hand, need to consume all the input before producing the output. An example of pipeline breaker is final aggregation, because unless you consume all the rows, you cannot be sure that you will not encounter a row that would update an aggregate value. Another example of a pipeline breaker is a sort operator, because again, you need to consume, you need to collect all the data before producing the final output. And the idea of the on-stack operator replacement is that you can start executing your query right away in interpreted mode and compile streaming operators in background. And once the streaming operator is ready, you can replace the implementation of an operator between the batch processing. Dealing with stateful operators with the pipeline breakers is more hard, because you need somehow to transfer the internal state and probably convert the internal state from the interpreted hash tables to the compiled hash tables. Obvious downside of this approach is that you need to maintain, to write, and to test two implementations, two sets of operator implementations, which is, well, it is up to each project whether this is a viable thing to do or not. Another thing that you can do is to use compilation cache. And for the compilation cache, this per operator separation comes in very handy, because you can use, for example, the quite compact operator code or even operator descriptor as a cache key, and you can store the compiled binary code as a cache value. However, the first iterations that we used showed that the cache hit rate was not as good as we expected. So there are a few heuristic things that you may do to improve the cache hit rates. One of the things that was quite important is extracting, let's say, constant literals into query parameters. So for example, if you have a projection of a+1 and a+2 without parameter extraction, you would end up compiling different pieces of code. However, in practice, just substituting this constant with let's say, value that is read from memory, that is also a constant, does not change performance much, but instead it gives you essentially a cache hit for every parameter value. Another thing that you might want to do is sort of heuristic expression and heuristic operator normalization, because there are a lot of commutative operators, and users may write a plus b and b plus a. And again, if we are using either just the text code or operator descriptor as a tree, these expressions would be considered different. So it is quite a complex thing to, let's say, convert every expression into some universal canonical form. But you can do some heuristic best effort normalizations, for example, to sort the arguments of commutative expressions in some way to get more reliable cache hit rates. Another thing that we employed a lot is using using cache persistence. The thing is, unless you change your internals, you can preserve the binary code representation across system restarts. And again, this comes in handy when you scale up and scale down your distributed databases. So when you start a new worker, you don't need to pre-warm the cache, because again, unless you change the operator implementation, you may reuse the compiled code infrastructure. And one of the last things that may be employed is moving the compilation out of the database worker process, because it gives again, let's say, scalability for the scalability and more predictable times for the code compilation, and the compilation itself, the compilation process, does not take resources from the query execution. So again, this separation is convenient, especially when you're running a distributed systems. One of the things that's also popular when it comes to operator execution is operator fusion. And the idea behind that is that instead of compiling code for each particular operators, you may take a look at a pipeline as a whole and generate code that would execute the pipeline itself. So here we can combine aggregate, project, and filter into one tight loop. And again, I would say that opinion on operator fusion is quite controversial. On one hand, it gives you a tighter loop and more opportunities for optimizations. So probably the fused operator may execute more efficiently. But on the other hand, since you're now combining multiple operators, it decreases your chances of cache hit if you're using cache. In our opinion, it decreases the observability of your system, because now let's say, it's harder to understand what exactly causes slowdown, for example, how many rows were filtered by this particular operator. And it was also noted by some of the system developers that such operator fusion may cause compiler not to choose vectorized instructions. So instead of more optimal code execution, you get slower code execution. One of the benefits that we saw when executing the JIT code is that it gives you great flexibility on how you deal with the code. For example, you may on demand introduce arbitrary performance counters that are built into your relational operators. For example, you can collect information about hash table collision statistics, number of skips in an open address hash table, and so forth. And since, again, the code is generated at runtime, you may opt in or opt out for these performance counters. So essentially, this is a zero overhead observability instrument. Since, again, you're compiling code for each particular operator, you can omit additional symbols and use any profiling tools to get insights into the particular operator's statistics, which also gives you an opportunity to map the statistics of these particular operators to the original plan. And the final thought, I would like to talk about tooling that you can use probably in your projects, because again, from what we see, the main benefit of JITing is code specialization. And if you're working on any compute-intensive project, you may benefit from the JIT. And depending on the project, we saw different frameworks being used in production. I think one of the most popular and famous and powerful instruments is LLVM. It's a C++. Well, essentially, it's a compiler infrastructure that may use different language frontends and has many backends, and it can generate code for multiple platforms. And you can definitely use it to build just-in-time compilers. In Java world, besides the regular Java compiler that you may invoke in runtime, there is a great ASM framework that is used, for example, in Presto and Trina projects to generate certain parts of the query execution pipeline. And it is a quite low-level infrastructure for emitting the bytecode instructions. And there is a Janina compiler that is used, for example, in Dremio and Apache Calcite to generate runtime operators, and in Calcite, if I'm not mistaken, it is used to generate statistics handlers. So yeah, in our experience, JIT is not as, let's say, is not as hard and scary as it may look like. And thank you, and I can answer your questions if you have any.
Thank you, Alexey. You deserved your water. You can drink now.
Thank you.
Guys, please raise your hands if you have questions, and please ask them. So we have one question on the first row.
Could you explain, are you writing your custom database, something in memory database, or are you using this approach to some standard databases?
Essentially, well, at Querify Labs, we are not building our own product. Instead, we help other companies who are building their own databases, and we help to build both query optimizers and the query runtimes. And yes, this is what we did, for example, to build a custom analytical platform. Was that your question?
Any more questions? So, first row again. А можно нам свет в зале, пожалуйста, извините? If we could have the lights in the hall, please, to see the crowd. Yes, please.
Okay. Thank you for your presentation. And now it's 21st century, and of course we deploy our application in clouds. And my question is, did you try to use some JIT compilers deployed in cloud like service, as service?
You mean JIT compiler as a service?
Yes, correct.
Yes, it was a prototype, but yes, it was a viable approach. So essentially, it is doable and it works, and yeah, so it's.
Was the result better?
Was the result better? Well, define better. The reason why we wanted to move the compiler out of the process is, let's say, more predictable CPU load on the query nodes. So we didn't want to consume to skew the CPU consumption towards the compiler threads. And well, yes, in that sense, it was better.
Thank you. Yeah. Thank you for your presentation. And my question about numbers. Do you have some comparison between traditional non-JIT databases and your approach with JIT compiling?
So yes, the question is about how much faster the JIT code compared to the interpreted code. It pretty much depends on the operator and the extreme. Well, I don't have any numbers on hand because again it depends even on the data set and on the specifics of the expression. And I believe I can craft a benchmark, for example, with global aggregate, where compiled code may be up to 10 times faster than the interpreted code. But in general, we saw on simple, for example, on simple queries, up to 2x to 3x speed up.
Please.
Thank you for your talk. You said that you use, you plan for optimization in compiler. And how do you handle when it not comes, when it, let's say, not goes as expected, when you optimize with size and with speed?
Sorry, I did not catch the question.
For sure, optimization has some influence on compilation and the result. And how do you handle it? How do you like plan for it? Because you already do some optimized code, and do you like turn it off, or you plan for some like for what compiler will do with your code when it's compiled?
Well, in this regard, I think it is the difference between the transpilation and IR generation, because in transpilation you completely trust the compiler, and you just give it a bunch of code and believe that it would generate the most optimal code that you would expect. If you do not trust the compiler, you need to run all the optimizations manually, and then this is when you resort to the IR generation. So this, again, depends on your resources and plans and goals.
There's the microphone walking towards your direction. Yes.
Yeah, thank you for talk. What about bugs because of JIT layer into the, I don't know, modern databases? How often the problem in JIT, not in other code, other core code?
So you mean what is the input of the JIT speedup, you mean?
No, not input. How often we have problems because of JIT? In practical, in your job?
In our experience, so I assume that the question is whether the JIT itself produces incorrect results. In our experience, well, we did not encounter compiler bugs. So usually it was the issues in the generated code, and it was normally can be caught using the testing.
There's one.
Yeah.
So this would be the last question, and then we have a good tradition to give a prize for the best question, so you'll need to choose.
Hi, thanks again for your lecture. JIT sounds pretty much like a silver bullet, right? But not everyone is using it. Can you try to explain why?
Yes, we spent all our lives looking for silver bullets.
Yeah, right.
And now you need to say no again.
Yeah, I think this is the best question. Yeah, of course, JIT may look like a thing that can speed up the query a lot, but again, you need to understand the specifics of the database or use cases that you encounter in your database. And I think this is one of the trends that we are going towards, and the trend, I think it is called composable systems. When you have different building blocks, for example, you can build your own query optimizer, you can get Apache Arrow or Velox to get your own query runtime, and you can compose them in order to, let's say, to create a system that would be optimized for your particular goals. And why JIT is not a silver bullet? Because there may be issues in other components. For example, your optimizer, your SQL optimizer may produce a very inefficient order of joins. And no matter how fast your code runs, if you produce, for example, billions of intermediate results, you will never run fast. The other thing is that instead of going for JIT, you can opt in for materialized views. And for example, for most of the queries that you run in your system, you may create a set of easily maintainable materialized views, and then again using those views may be much faster than running even JITed code but on the raw data. The question is, however, whether your system would be able to automatically understand that this particular view can be substituted, but this, again, is another subset of problems in database engineering. So yeah, I think that it is not a silver bullet because there are many other opportunities, and you may choose other paths to execute faster.
Thank you very much, Alexey. I am reminding you that please scan the QR code and please rate the talk so that the program committee would be smarter next time, and so that we could collect all the best talks we did. So, Alexey, thank you very much. A big round of applause.